So let's have a look at these two more sample problems here that you guys have been working on together. Not a lot of fluff in the question. It's pretty much just straightforward data kind of thing. I've drawn a picture here to indicate it. As always, start with PI is equal to PF. If you want, I'm quite happy if you want to skip this step. If you feel the need for this step, that's fine too. I'll write it up here. So that would be MAVA plus MBVB is equal to MAVA prime plus MBVB prime.
So it's okay if we go straight to that, right?
Oh, like skip this one right here?
Yeah.
I guess. Yeah, if you want to do that, sure. I would suggest at least do one of those two, right? Just to sort of get yourself going in the right direction. Okay? So this would be 6, this would be 4. It's going, looks like they're going east. Mass of the second ball is 2, the velocity of the second ball is 3. And again, if some of you want to complete the left-hand side before you finish the right-hand side, that's fine too. Like if you want to just get the arithmetic out of the way, you can do that. Remember, the masses here are not changing, right? So that's going to be 6, and this is going to be 2. And the velocity of A after, make sure you've got it the right one. Yes, that becomes 2. And then this one is VB prime. So 12 plus 2V prime. Oh yeah, and this is the problem with doing the math ahead of time, right? I'm going to take that 12 to the other side. That's going to be 12 plus 6 is going to be 18 is equal to 2VB prime. So VB prime is equal to 9 meters per second. Did you get that? Excellent. See, they're not really that hard, are they? It's the positive is good enough, yeah. Awesome. Okay. The last one here, opposite directions. So the only thing that's really changing here when there's opposite directions is what? There's going to be a negative somewhere, right? Okay. So a 1 kilogram ball with velocity 3 meters per second east. So 1 times 3. Strikes a 6 kilogram ball moving west with a speed of 5. So this is going to be 6 and this is going to be minus 5, right? I'm not going to fall for this trick again. And leave it like that. This is 1. If the final velocity of the 1 kilogram ball is 9 west, so that's going to be minus 9. What is the final velocity of the 6 kilogram ball? So 6 VB prime minus 9, 6 VB prime. I got 3 minus 30 is minus 27, plus 9 is going to be minus 18. VB prime is minus 3. Did you get that? Oh. Yeah? Yes? That would be fine too, Joy, yeah. Although it would, you'd have to get this first, wouldn't you? Like math.
Yeah, like I got the negative.
Yeah. And then wrote it, yeah. Oh, you wrote it like this, you mean?
Yeah.
Yeah, that's okay, sure. Yeah, that's fine. Okay, so I think we're in pretty good shape. Okay, so explosions. What's the deal with explosions? Any real difference?
Go farther.
Well, let's go through this here. Common examples of the conservation of momentum centered around 2 or more objects colliding in the absence of external forces. Another twist on the example of a collision would be the idea of a reverse collision or an explosion. If you videotape an explosion and play it backwards, it looks like a collision. And likewise, if you videotape a collision, play it backwards, it resembles an explosion. If we look at the case of a cannon being fired, we find there is a force of the gunpowder exploding, creating a force of the cannon pushing on the cannonball, and the cannonball pushing back on the gun. These two forces are equal in size, but opposite in direction. If any forces that are external to the cannonball system, such as weight and friction, are removed, then momentum must be conserved. In the example at the left right here, The external forces have been removed by placing the cannon on frictionless surface. In the beginning, both the cannon and the ball are at rest. As a result, the total momentum before the explosion is zero. Do you guys know what that funny looking symbol means? That is the Greek letter S, I believe. It's a, they call it sigma. It's a capital sigma, and it simply means sum. And professors love to use sigma instead of net. Okay, so it means like the net sum. So this really means the overall total momentum, the sum of all momentums. Since the total momentum of an isolated system means no external force is conserved, then the total momentum after the explosion would also be zero. So the only real difference is, if I just go back to here, instead of there being momentum on the left-hand side, what is the momentum on the left-hand side? Dan, you should be looking up here. It's zero. In fact, you could even argue that collisions or explosions are actually easier because the left-hand side is going to be equal to zero, and you don't have to do any of this. I think I did run this off. Let me look. You have the same handout there now that I have up on the screen, albeit still making its way around. So again, that funny looking symbol means the sum, so the total momentum before is equal to zero. Now, at the bottom of your page, you see this bunch of junk. Right, Dan? Let's just decipher this a little bit here. So mathematically, the explosion looked like this. So this is sum of momentum. Just on top first. Yeah. Sum of momentum is equal to sum of momentum after. So this is just another mathematical way of writing Pi is equal to Pf. Okay, I just ignored that sigma thing. Okay? And then they did the next step. P cannon plus P ball is equal to P prime cannon plus P prime ball. And then they did substitution. You'll notice that over on the left here, all that substitution boils down to a big fat zero. You'll also notice that on the right-hand side, it boils down to a big fat zero. How come? Because momentum is conserved. Now, in this particular case, they gave you the answers, right? There was no question here. They told you this is 100. They told you this is 5, and they must give them some velocity, I guess.
Oh, this is only on a
Somewhere along. It's on a frictionless surface. Exactly, right? Because generally, cannons don't recoil backwards like that, right? Usually what they've got is the base is attached, right? And the cannon itself recoils backwards. It slides back. And you've seen that maybe even in Remembrance Day, right? You see that sort of recoil kind of thing. Okay. You'll notice that the cannon has a new velocity that is in the opposite direction of the velocity of the cannonball. Remember that momentum is conserved, not velocity, because the mass matters. So the mass of the cannonball is 20 times smaller than the mass of the cannon. As a result, the velocity of the cannonball is 20 times larger. Consider what would happen if you had a cannon with a small mass and a ball with a large mass. What would happen? If the cannon was small and the ball was big, the ball wouldn't go very fast. In fact, it would be the cannon that would become the projectile, right? Joey, put the phone away. This concept of momentum being conserved in an explosion is true for an explosion along a line, one-dimensional, an explosion along a plane, as in two-dimensional, or an explosion in free space, three-dimensional, something like a hand grenade, right? If you toss a hand grenade in the air, don't do that, by the way, don't try that at home, right? And it explodes. If you took all the individual momentums and added them up, well, they would equal the original momentum of the hand grenade as it's flying through the air. Do you have this in the bottom of your page as well? Suppose an example, the 5-kilogram cannonball moves with a speed of 25 after the explosion. How fast will the 100-kilogram cannon move backward? Do you want to try that one right there, or do you want me to do it? Do you want me to do it first? Okay. Do you want me to do it in their format or in our format? Our format? Okay. So it would look, again, something like this. Pi is equal to Pf. But what is the momentum to begin with? Zero. Do I even need to worry about any of that stuff? I say no. That's just a waste of good pencil. Mass of cannon, velocity of cannon, plus mass of ball times velocity of ball. And I guess technically I should put primes after here. a 5 kilogram cannonball, so that's this one here, moves with a speed of 25. How fast will the other one move backwards? So this is 100 times velocity of cannon prime. Yeah, because, well, no, not always. Only if the initial thing is at rest to begin with, right? If it's not at rest to begin with, then yes. So here I've got 100, 0 equals 100 V cannon prime plus 125. So the velocity of the cannon prime is going to be minus 125 divided by 100, or minus 1.25 meters per second. I think they're actually easier because that left-hand side doesn't exist. Does that work for you? Yeah. The is already moving? Oh, well then, there's still going to be some recoil, right? And that's why they build, like, if you look at cannons, the newer style ones, like a mortar kind of thing, right? They have that big base that they can move around and they lock it down. And then the barrel of the cannon actually moves back, absorbs that recoil. So yeah, no, it still has to happen, right? Yeah.
Could we have to shoot the thing further if it had no recoil?
It has to have recoil. It can't not have recoil. Momentum must be conserved. If there's momentum forward, there must be momentum backwards. They can do everything they can to absorb it somehow, right? Or reduce it, but there still has to be something. Maybe not reduce it, but disperse it. It could become heat, yeah. I mean, if they increase friction, right, then it becomes heat. Okay, here's what I'm going to suggest. With your group, flip over your big piece of paper and try the firecracker one. And then I'll do it for you. Okay, here's the answer for the firecracker. Did you get 0.6 meters per second? Yes? Yes? Okay, give yourself a hearty congratulations. Now let's try Mr. Potato Head. Now, as I said here, the difference with Mr. Potato Head is that he's already moving. So it's going to complicate things. Right? In this case here, and you can sort of subscript it however you want, I'm going to say mass of potato, velocity of potato, and then I'm going to talk about different pieces, right? So then I'm going to say M1 V1 prime plus M2 V2 prime. You can subscript it however you want.
You have to.
No, I mean in this case here, you can keep them separate, right? It's really only when you get to the two-dimensional stuff that it really starts to, you need that just to keep organized kind of thing. I wanted to introduce that. Okay, so we've got a 6 kilogram potato. That's one big potato. It's like, like a size of a medicine ball. 4. Here we've got 2 pieces. One is a mass of 2 kilograms, moving at 8. And what is the velocity of the second piece? Now, they don't come out and tell you the mass of the second piece, but I'm hoping nobody got stumped on that. It's just 6 minus 2. So really, hey, is this hard? It's just a setup, right? Once you've seen it. The units. So 24 minus 16 is going to be 8, is equal to 4 V2 prime. So V2 prime is equal to 8 over 4, or 2 meters per second. Jake, did your group get that? Yeah? Any other groups get that? Okay, there it is. Alrighty. I'm going to give you a couple of pages of work. Ready? Yeah, I was. I suppose. I knew that I had this stuff ready. I thought that. Always peaceful. done with the big sheet now, yes. You can throw it away, you can take it home, put it on your fridge. You can make a paper airplane. Did I? Concussion. Okay. You have the remainder of this period. I realize there's not a lot of time left. You have all of Monday's period. I'm hoping to get here by about this time on Monday. If you need Monday's time to complete some filming or anything like that, use that as well for the power video. You've got it. Do what you need to do. I'm not really sure what we'll do Tuesday, but there's really not a whole lot more. Oh, two-dimensional, I guess. That's going to take a couple days. She might. I really keep. This is math. Well, you're talking angles. Two dimensions. Just be glad I don't need to do three dimensions. Fourth dimension? Yeah, this is called time. But I don't have time. All right, enjoy. Have a fabulous weekend.